Right. Hello, everyone. My name is Andrew Isaacs. Today we're going to be talking about grid forming as part of the UNIFI series of lectures on grid forming technology. This is an introduction, so we're going to start a bit slow with this topic of the question of why grid forming even exists. This lecture was or not a lecture, I guess, presentation was originally in some form presented at the IEEE general meeting in this summer in Orlando. And Ben Koropowski asked me if I would sort of revise it and do a similar one for UNIFI. And so that's what we're doing. So if you've seen some of this before, that's the reason I'm borrowing some of that material. Maybe I'll start by just introducing who we are as a company. My company is called Electronics. We've been around for a little over 20 years. We do studies and simulation. I like to put this slide on here just to show all of the people that do all of the work here. This is all the folks that do all of the hard work that I get to present sometimes. So we're going to start, and I should also mention that you're going to see at some point my hair suddenly grow longer and my shirt change color. And the reason for that is there was an error in the original presentation of this, and it had to be re-recorded, just the first few slides. So this is a re-recording. So if you've seen this in the past, then this might be slightly different, but okay. So through the course of this presentation, we'll talk about the reasons for grid forming. We're going to take kind of a meandering track through the presentation. First, we're going to ask, is there a problem? In other words, what are we even talking about? Problem, what is the problem? We're going to take a little detour and talk about what we mean by grid forming, the GFM acronym. How do we define grid forming? What are we all talking about? Just so we're all on the same page. And we're going to talk about some solutions to the problem and how we could solve this problems. And then why is the GFM solution kind of a special opportunity or a killer app that we have right now to deal with some of these issues we're having in the power grid. And then we're going to take a little detour at the end to again talk about what other problems we can solve with GFM, some other applications that are coming. Okay, so I want to give two disclaimers before we get started. The first one is regarding SCR, or the short circuit ratio metric. We're going to talk about short circuit ratio a lot in this presentation. And it's a very helpful metric. It's been around for a number of decades. It's used for HVDC design, and in the early years of interconnections of IBRs, it was really useful. However, these metrics, so SCR and also other corresponding metrics, have very serious limitations that we won't go into today, but they essentially will begin precluding their use in many of our studies. So modern high penetration scenarios are not conducive to the use of SCR. So the caution here, disclaimer, is use SCR with extreme caution or don't use it at all. The second disclaimer is about the presentation itself. This is really a prelude to a lot of very technical presentations on grid forming. I'm going to keep it really high level, use lots of cartoons, basic concepts. I'm going to use previous analogies and cartoons from other presentations, and I'm going to be, as I say here, borderline irresponsible to the degree that I simplify this technical material. So, if you're looking forward to highly technical stuff, tune in for the rest of the series, and today will be a little simpler. So I'm going to start with a really rough analogy. So a thought experiment. What if we were told by the politicians and those who sort of make the rules that all cars and trucks will be phased out by 2045, and we're only going to allow boats in the world because we know that the cost of shipping goods by water is much cheaper than air or truck, and we really, really like boats. Okay, so that's the challenge. Engineers, get to it. Okay, we're not gonna use roads anymore. You have a couple of decades to figure that out. So, you know, when we're talking about this energy transition or renewable transition, sometimes it feels a little bit like that. Like boats are kind of like our IBRs, our renewable plants, solar and wind and batteries, and the trucks are kind of like what we're used to. They're the you know, the conventional synchronous machines and thermal plants, and it feels a little bit overwhelming in that way. Like there are so many problems that you can't really even explain at a policy level to people, that this doesn't really, you know, they don't work fundamentally in the same way. It's a different set of physics that we're using, and it's a different, or at least physical problems, and it's a different set of constraints that we have that require fundamental changes to the way that we do power systems. But that's the challenge in front of us, and we can do it. But we're going to need to, you know, be creative. I'm not going to deal with all of the challenges that we have with this transition. You know, you're aware of some of them. We're just going to talk a little bit about the control challenge. So what is the problem exactly that we're talking about? So when I started thinking about this, I decided to pull up an old presentation from 2003 that I did to an organization called AWIA, which is, I think, now changed to something else. It was American Wind Energy Association. They did huge conventions and so on about wind. This was 10 years ago, and already this was sort of on the radar for people, I would say as long as 15 years ago. We were talking about connecting wind farms into relatively weak systems. And so I was doing this presentation on SCR. You know, the size of the wind farm relative to the strength of the system is a metric we can use. Relatively weak is low SCR, relatively strong is high SCR. And we've you know, gotten used to this short circuit ratio now for this purpose. But at the time we would say, you know, less than 1.5, power electronics can't maintain control, wind farm won't run at full power, conventional study tools don't work very well. Less than 2.5, you know, you might have problems, and then higher than 2.5, probably the wind farm is going to be performing predictably, but you have to be careful. And I had all kinds of disclaimers around all of that. So I think that's where we're going to stop, right, Anita? Or sorry, Diane? Weak, and a high short circuit ratio was relatively strong. If you had too low of a short circuit ratio, you would have trouble with controls. So we would say the wind plant at the time, you know, there wasn't much solar around, but the wind plant would have disproportionately large capacity to sort of move its local system, and it would cause trouble. It would have difficulty, and you could see these I had disclaimers, all over these. I remember that, you know, less than 1.5 might be considered low. You know, conventional study tools might not work, and power electronics wouldn't work. Less than 2.5, you might have trouble. Higher than 2.5 might be, you know, probably okay. And this was coming out of very early studies that we were doing, you know, maybe 15 years ago, that were saying, okay, if you connect these wind farms, big wind farms, into long, skinny transmission systems, you might start to have problems with your controls as the short circuit ratio dropped. And it was a very useful, you know, effective metric. We could start to see small signal instabilities growing. We could start to see control interactions happening, and wind farms interacting with the system and oscillating and so on. So this was, you know, the warnings that were showing up 10 to 15 years ago in our power systems. We were starting to see these low short circuit ratio problems. So short circuit ratio works really well when you have a single plant at the end of an impedance connected to a strong system, right? But as we've kind of gone beyond that now. And what you can see is when we look, I'm sorry, I'm behind a slide again. So these were the problems that we would see in the system. You could either see small signal instability growing, or short circuit ratio between 1.5 and 2.5. You could start to see these oscillations. So what we can see, you know, in the last, Wei said I've been here for more than 20 years. I think that's about right. So my first job at Electronics in 2003 was to study an interconnection of a wind farm. So you can see from these charts, 20 years ago, the share of primary energy in North America from solar, essentially zero, and wind was also essentially zero, and it was just starting to climb. And you could see around when I did that presentation around 2013 or so, solar was just starting to get built. We were building some in 30 megawatt plants. I think there was one in Colorado that was 30 megawatts. That was the biggest at the time in the world, or at least in North America. By 2013, wind was steadily climbing, right, and continued to climb for some time. And now you can see both the trajectory and where we are in proportional. I'm not sure if these are exactly accurate numbers, but you can see the shape of these since that time. We've gone to a new place altogether. And the problems are similar. They're the same types of oscillations that we saw, 15 years ago, but now, the first, I think, SSCI problem observed was 2009 with wind farms. Now there's a huge amount of effort going in every day into subsynchronous control interaction studies and mitigation and dealing with issues with that. There's also in the last 4 years, at least, or last 2 years, I should say, at least 4 of these NERC disturbance reports relating to connection of IBRs, right? This is either oscillations or ride-through failure or interactions between plants and causing trouble. We see this, large interconnection, very tiny interconnection, but still interconnection level studies in Australia and Hawaii that are showing, okay, this is where we're going. We're going to 90% renewable, sometimes 95. This is what it looks like. It's not stable, essentially not viable as proposed. And so, these are the same type of things we've been seeing coming, but now not only is short circuit ratio not a great metric anymore, just because it's so hard to, find that, single plant radial strong system. It's now sort of everywhere, but it's the same essential issues. We're having trouble with ride through, we're having trouble with oscillations, trouble with interactions. So I'm going to take a little sidebar here, interrupt the flow of the sort of the history lesson here, and we're going to go to just talk about what we mean by GFM for the purposes of this conversation. So, and I've presented similar slides to this many times, so if you've seen this before, it's okay. And it is oversimplified. Remember, disclaimer 3 down here at the bottom is referred to disclaimer 2. We're not going into a lot of depth here. What is exactly GFM and all the ways you can do it? But the essence of it is illustrated by this little test system in the top right-hand corner, where we have an IBR connected to a grid and a synchronous generator that we're going to open. So we're going to disconnect the synchronous generator and leave this IBR connected to the grid. So we're really talking about grid-connected resources, for one thing. And we can see how they compare between grid following, conventional controls, and grid forming controls. So assuming this is a battery, probably, what we say is that it holds a constant voltage phasor in the subtransient time frame. So if you don't like subtransient, you can say very short time frame or near instant time frame. But the idea is that if you look at the terminals of this battery, that V1 angle theta 1 immediately after the event at T1 is not going to change, okay? And it's going to definitely change over time, based on what we need to do with the controls, but the essential grid forming characteristic is that it's constant. And so when you have that T1 happens with a grid following device, it is not constant. It tries very hard to follow the local power or follow the power order that it has, and it adjusts its theta 1 instantly. It tracks the grid angle using very fast phase lock loops and other mechanisms. It tracks the grid angle so that it can hold its power constant. And after that time, it goes to whatever droop or other controls you want to do. But in that moment, the theta will change, as opposed to grid forming control, where in that moment, theta 1 does not change, and you get a consequential step change in current, especially in active power, but also reactive power. So that voltage phasor defines what the currents will be out of the device. So the outer loop controls, the slower stuff, may be very similar to GFL. You get the same steady state result, assuming that you control it, in the appropriate way, but in the short time frame, you don't. So just a couple of other quick reminders about GFM resources. Grid forming does require energy and current headroom in order to get that effect, that constant phasor effect. And there are a number of ways that we can do the controls, and you're going to see lots and lots of discussion about that in this series. And a lot can be done not only in how you do the actual voltage phasor control, let's say, but also what you do to shape the response afterwards for specific needs. You can be very flexible about what happens after that GFM effect. The third thing to remember is that especially for devices like batteries, where you have energy and current headroom, the hardware is generally quite similar between grid forming and grid following. Fourth thing to remember is that generally all the things that you can do with grid following, we should be able to expect that from grid forming as well. In other words, we're not taking anything away, but with a caution that you have to be careful how you write requirements, because the inherent nature of these devices is a little different. And so if you've written your requirements to be very specific about exactly how a GFL responds, then you may have a problem. But functionally, to get the things we want out of the power system, we should be able to do that with GFM. Just another quick zoom on that figure, and a reminder that battery energy storage is uniquely suited to grid forming, right? And that is because generally it's easier to provide that current and energy headroom if you're not dispatched at the maximum output. So if you have current and energy headroom, which is what is needed for that grid forming effect, you more naturally will be able to obtain that with a battery. So coming back, it turns out, and we're not going to go into all of the details of these at the moment, but it turns out that if you provide that type of control, that grid forming effect is very useful. It provides a very significant stabilizing influence in many systems. So many of those issues that we struggled with for the last 15 years, weak system issues, SSCI even, ride through, it's maybe a separate one, but if we think of the, some of these stability issues, there's a lot of inherent stability provided by this type of control. And so when we look at, I just put a smattering of results here, and some of these I've used with permission and some maybe not. So apologies, I've put references in here, but for example, in the Hawaii case, the trace I showed you before, where they had load shedding and instability, switching the battery over to grid forming stabilizes everything. Another case down here, this is a real world event that was recorded, and then was, they changed one of their batteries to grid forming and then repeated the same event by accident. I mean, it just happened again, and they managed to capture what that looked like, and it was stabilizing. We've got some very recent, call it hot off the press regional studies that EPRI's working on. And I know that I said ask your Deepak Ramasubramanian here, but you can see that with the grid forming, there's significant improvement made to the response on a regional basis. So, and this, I know that you may have your own examples of this, but it's fairly straightforward to actually show this inherent benefit from these controls. Okay, so we're going to pause and look at this metric that I told you not to use. Okay, so this is a cartoon only. Please don't use SCR or be very careful with it. If we just consider what SCR was good for, right? We're going to try and understand what impacts a quote unquote weak grid, understanding that a weak grid may be a large interconnection if we're just talking about short circuit ratio. So if short circuit ratio is a proxy for strength, okay, and the strength of the system is going down, and we think that maybe if the system is weak or the strength is low, then you may have a higher chance of things like control interactions and oscillations and ride-through failure. The short circuit ratio is defined by the short circuit MVA on the top and the megawatts of the inverter-based resource on the bottom. So what is happening in our system? We have synchronous condensers. Those are good. That adds to the numerator here, and the short circuit ratio will go up. Thermal generation also makes it go up. Grid forming IBRs and grid forming HVDC and FACTS will make it go up. New transmission will go up. Control tuning, I colored kind of green and red. You know, it depends what you do with your controls, but maybe it's on the top or on the bottom. On the bottom, though, we've got some real problems. We've got retiring thermals. So that's coming out of, I should have drawn that arrow actually going to, you know, to the top actually. And the grid following IBRs are coming in, you know, hot and heavy. They're coming in really thick, and the grid following HVDC and FACTS as well. So these days, we are really turning this top number down and turning the bottom number up really fast. Now, we have an interesting thing happening here that if you think about the batteries, we've got, these are highlighted. Batteries are just IBRs. Currently, we're dumping them in really fast into the bottom of this equation. We're dumping lots and lots of batteries into the system, as well as, you know, PV and wind, HVDC and FACTS. If we just make this control change, we, you know, change it over to grid forming batteries without really changing our hardware, we right away change, we flip that equation upside down, and we start putting the batteries into the numerator of this SCR equation and make our system strength, or our proxy for system strength, start to go up. So we have an opportunity. We have a unique kind of killer app, or an opportunity to increase our system stability in a huge way. I found this plot from the Energy Information Administration. They have all kinds of wonderful data that they put out every year. This is a draft version that they have qualified and all of that, but this is essentially the 2023 numbers. You can see what's happening with batteries going into the system. So the historical batteries going in, we had, you know, nearly 10 gigawatts of capacity, with nearly half of that in 1 year. And then doubling again, 2023, this is planned, probably basically already in service. And then 2024, nearly doubling again. So we're looking at 30 gigawatts of capacity by the end of 2024. And you can see where they're going, mostly in California and ERCOT, but everyone else is getting on, and these numbers will start to grow there, presumably in a similar way. So
sorry for the interruption, Andrew.
sorry, one behind again.
Thank you. Okay.
Thank you, Wei. Appreciate it.
Thank you.
This is a flaw in my system here. I'll just give you a moment to look at this. So, yeah, looking at this data from the Energy Information Administration, you can see how year over year, these batteries are coming in extremely quickly. So, this is an opportunity, but how long will this trend continue to go up at this speed is a valid question. You know, certainly battery technology is getting much, much cheaper. Inverter technology is getting, you know, better, but all of these batteries currently, all the way up to 2023, likely into 2024, with very few exceptions, you know, very small systems or people who are doing, you know, test projects, are essentially going in as grid following resources and going into the denominator of this SCR equation. So this is an opportunity, right? And it's, in my opinion, bordering on a missed opportunity. We have all of these batteries, which could be assisting sort of in general our stability issues that are coming, are essentially coming in as problems rather than as solutions. Okay, so with that, sort of the big picture why grid forming, I wanted to talk a little bit about some other things. You know, what else is grid forming useful for? What else can we use it for? It's not just good in general, it's good in some very specific applications and can be applied, you know, more surgically as well. For example, increasing transmission capacity in local weakened regions. So this would be your classical, you know, weak grid. And this was an actual case that we studied where you have a grid following IBR, a large wind farm connecting into a transmission system. And of course, in North America, we plan for the loss of one element. When we lose the big element, the big transmission line out, the plant is left connected radially through a weaker path. And two things happen. One is that you overload the path. And the second thing that happens is that you have too weak of a system and the plant will go unstable, the controls will go unstable. So this is a perfect application for a grid forming battery. Applied correctly, you can provide your operators enough time to redispatch potentially. You can absorb the extra active power to avoid an overload, but also provide system strength that allows you to essentially keep the controls stable. So this is like a catch for this loss of circuit. So you can see the before and after traces are the grid forming battery was very effective. This is one I want to continue to highlight because it's, I think, very important in our current environment in North America, especially in some regions, California, some parts of the West, and then certainly in the Texas system where we have so many series capacitors. Grid forming has, for those of you who are familiar with frequency scanning, what we're looking at, or who are not familiar with frequency scanning, if you look at this plot here, it's kind of a simplified plot. We're looking at only one thing here. We're looking at resistance plotted with frequency. So it's, you know, there are other things to look at here. And for now, if you don't mind humoring me, just ignore kind of the middle piece of this, the 50 to 70 hertz. Don't worry too much about what's happening in there. You know, maybe I'll just take this band here and just neglect it for now. And you can see that you have without any effort, okay, just taking an off-the-shelf grid forming controller, you get a resistance characteristic that is essentially positive throughout this range, okay? And that means that we're effectively adding damping into the system. So for subsynchronous control interaction studies where we have wind farms and solar plants and batteries interacting with series capacitors and causing serious resonance issues and, you know, operating constraints and project delays and all these things, we can now be a part of the solution, okay? That these grid forming batteries add damping into the system. But not only that, with relatively minor control changes, okay? So this is, again, not hardware, just controls. We can shape these responses and provide extra damping. So we can actually tune these controls to effectively mitigate existing subsynchronous control interaction stability issues. And this should be huge news for, you know, wind developers in Texas, for example. This is a huge pain in their neck right now, this SSCI problem. So grid forming can be a part of that solution really effectively. This was demonstrated. This is my colleague Lucas Unruh who is working on this. But this is demonstrated in just a test system here. You can see the wind plant and a 50 megawatt grid forming inverter. So the wind plant can be scaled. And then we've just got a radial series capacitor, series compensated transmission line. As you increase the power of that wind plant, eventually, because of that SSCI instability, you start to go unstable at around, like, say, 320 maybe megawatts. It starts to go unstable just in the small signal domain. If you turn on these controls, if you add a grid forming device with no extra controls, you've added enough damping into the system, just this 50 megawatt grid forming battery, to get your active power up over 400 megawatts with no, not even trying. So this is a huge change in essentially hosting capacity. And then if you touch the controls, you start to tune them and tweak them, then you can go even much higher. So this is a 200 megawatt increase in active power transfer capability with only a 50 megawatt grid forming battery. Another application, if you need extremely fast frequency response. So, there are a lot of people want fast frequency response and all kinds of frequency response, but if you want very fast frequency response, you can have that with grid forming. So in some places, for example, in the Hawaiian market is a good example because it's so extreme to be able to identify this, but if you have very high DER penetration connected in a fairly short, small area that's serving a lot of your load, if you lose all your DER, you can materially impact your frequency. So if you, for example, have a fault and all of your DER blocks for maybe half a second or it goes away, you lose 50 to 70% of your resource. And the frequency you can see on the bottom right, frequency just goes through the floor and you start to shed load, right? Ordinary fast frequency response is not fast enough for this kind of response. We can't do it with grid following, certainly. This top left plot, this just, you don't get any energy. Assuming it, doesn't do momentary cessation, even you would get even less energy. A synchronous condenser, you get a little bit of help. You get this spot here, you get a bit of energy, but then right away, whatever you give, you have to take back away. And then if you have a synchronous machine, maybe you get that back over time. You get this fast frequency response, but by that time, you've lost your load. So fast frequency response isn't good enough. But with a grid forming, very fast frequency response, you get this chunk of energy right here, which is so valuable for those systems. It can keep them together. Another application, and this has been done now in certainly in at least one place in the US, the Mackinac HVDC link and ATC system, and maybe others, certainly others being planned. But you can use HVDC, so voltage source converter based HVDC can essentially be a pipe for system strength now. So you can use a grid forming converter in a weak system and use the other side to provide the energy, the strong system to provide the energy to basically give you that headroom, energy and current buffer on the grid forming side. So you can pipe that system strength from one part of the system to another very effectively. And then one last sort of cool application for you here is that you can use, small creative applications for these. So these are more island systems, but now you can power islands very effectively. So if this sort of, we'll call it a toy system almost, is you have an electrolyzer behind a DC link, and you have a wind farm, a big offshore wind farm or some other large, resource. It doesn't have to be particularly creative, any kind of solar plant. And if you have a battery in there to smooth that out and provide the system strength, the whole thing can operate with no connection to the grid. So, grid forming in this sort of application is not necessarily new. We've had, distribution systems and microgrids that have done that for a long time, but we can start to think larger with these plants as well. A couple of last applications that I'll leave you with. One is that, of course, you can use grid forming for black start if you choose to. It's sort of a special application, but it's inherently possible. You might have to add some extra control and extra hardware to do that, but you definitely can use those devices in system restoration. You can use it for load smoothing. So if you're finding systems, plants coming into your control areas with very strange or erratic loads, you can use grid forming to very quickly match those. System unbalance correction is another one that there's a few folks in the industry, wise engineers that I've heard speak about this topic for years now. They're concerned that what happens in our conventional power system is we are using these thermals, these synchronous machines, to absorb unbalance out of the system. So we may be, not transposing lines and having unbalanced loads, all the time in our system. All of that negative sequence unbalance gets essentially sucked into the system, into the synchronous machines. And we're now starting to turn off those synchronous machines, right? So as we do that, we haven't been paying a lot of attention to how much work those synchronous machines have been doing to balance the power grid. And we might find that we start to see significant amount of unbalance in our power grid. And one of the nice side effects of a grid forming converter is also that it will also absorb that negative sequence to the degree that it can with its ratings. I guess I can add more applications here. There are lots of sort of plus that you can add with the controls. So things like inertial response. If you want the grid forming inverters to provide specific inertial characteristics, you can ask the controls to do that. If you would like, I had another one in my mind. Anyway, in using the controls, there are a lot of things you can do to shape the response of the grid forming controls to give you other sort of ancillary benefits. Yeah, so I think I'll pause there. Not a very long presentation today, but hopefully a good one to whet your appetite about what we're going to be talking about in the UNIFI series on grid forming converters. So I'm going to turn this back over to, I guess, Wei, are you running this show? We can take questions or not, as you like.
Yeah, thank you so much, Andrew.